Hi, my name is Nguyen. I am a PhD candidate at Nanyang Technological University in Singapore. My supervisor is Professor Seng from Nanyang Technological University. My co-supervisor is Professor Douglas L. Jones from University of Illinois at Urbana-Champaign. My research interests are deep learning, audio signal processing, microphone array, and real-time signal processing. I'm happy and grateful to present one of our work at the DCASE workshop this year. I would like to thank DCASE organizer and the DCASE communities for an awesome playground for audio researchers like me to participate in the challenges and exchange ideas with other researchers. Today, I'm going to present our paper on the effectiveness of spatial and multi-channel features for multi-channel polyphonic sound event detection. Sound event detection problem requires the sound class prediction and the detection of onset and offset of a sound event. For single-channel sound event detection, single-channel log-mail spectrogram is arguably the most commonly used features. For multi-channel sound event detection, we have much more choices for input features. For example, multi-channel log-mail spectrogram and spatial features such as generalized cross-correlation with phase transform and intensity vector. So the question is, what are the best features for multi-channel sound event detection? For multi-channel sound event detection, multi-channel log-mail spectrograms are possibly the most commonly used input features. Multi-channel log-mail spectrograms are formed by stacking the single-channel log-mail spectrograms of all the input channels along the channel dimension. This stacking mechanism has several advantages. First, it is simple to combine features. Second, because most of the sound event detection networks are either use convolutional neural networks or convolutional recurrent neural network, the stacking mechanism does not require major changes in the network architecture. The only changes is the number of input channels of the first convolutional layer of the network. Several research have shown that spatial features such as GCC FET and intensity vector are also useful for multi-channel sound event detection. If you browse through the DCASE sound event localization and detection challenge, there are many sound event detection systems that stack GCC FET and intensity vector along the multi-channel log-mail spectrograms and input features. However, while working on the DCASE 2020 Sound Event Localization and Detection Challenge, we observed something quite interesting and irregular. The spatial feature degrade the sound event detection performance. One major difference between the 2019 and 2020 sound event localization and detection is that the 2019 dataset is simulated for static sources, while the 2020 dataset is simulated for both static and moving sources. So this observation motivates us to find out which features are the best for multi-channel sound event detection for both static and dynamic sound sources. To find out the answer, we are going to experiment with single-channel log-mail spectrogram and several multi-channel and spatial features. There are several ways we can utilize single-channel log-mail spectrogram of multi-channel microphone inputs. Here we are assume that the number of microphones is 4 for the simplicity of illustration. First, we can just use the single-channel log-mail spectrogram of one channel for both training and inference, ignoring other channels. Second, we train the model with single-channel log-mail spectrogram of the first channel. During inference, we use all 4 single-channel log-mail spectrograms as separated instances and average the inference outputs. Third, we train the model with all the single-channel log-mail spectrogram as separate instances and only use single-channel log-mail spectrogram of one channel for inference. Fourth, we train the model with all single-channel log-mail spectrograms as separate instances. During inference, we use all 4 single-channel log-mail spectrograms as separate instances and average the inference outputs. It is expected that the fourth method will give the best performance at the expense of longer processing time. Using all 4 input channels as separate training sample is equivalent to data augmentation, and using all 4 input channels as separate instances is equivalent to data and sample. Both these data augmentation and data ensemble are expected to improve the model performance. The multi-channel and spatial input feature that we are going to experiment with are multi-channel log-mail spectrogram, stack of multi-channel log-mail spectrogram and GCC FET, and stack of multi-channel log-mail spectrogram and intensity vector. The number of time lags in GCC spectrum are selected to be equal to the number of mail bands, and the intensity vector are passed through the same mail filter so that they can be stacked along with log-mail spectrograms. The SED network architecture that will be used is borrowed from the SED network of the two-step paper by Cao et al. The network consists of 4 CNN blocks followed by a bidirectional GIU and a fully connected layer. The SED output for each frame are the posterior probability of all the cell classes. We do not use any data augmentation technique in this experiment, and we use the same network architecture to evaluate the model performance with different input features. We use two datasets for experiments. One is the 2019 SELD dataset for simulated static sources, and the other one is the 2020 SELD dataset for dynamic sources. Both datasets provide first-order ambisonic and mixed-array format. There are a total of 4 input channels. The size of the training and test set are similar. The length of training and test set are 400 and 100 minutes respectively. Given the two datasets are quite similar, the hyperparameter to process the audio input for both datasets are almost identical. The sampling rate for the 2019 and the 2020 datasets are 32 kHz and 24 kHz respectively. The evaluation metrics for SED are segment-based error rate and F1 score. The segment length is 1 second. These metrics are widely used for cell event detection. Here are again the summary of all the models that we are going to evaluate against each other. There are 4 models for single-channel input features and 3 models for multi-channel input features. The prefix X is a short form for single, while the prefix M is a short form for multiple. The number of input channels for all the single-channel features model is 1, while the number of input channels for the model that use multi-channel features are much higher. These models that use multi-channel features are slightly larger than the models that use single input channel features. The experimental results for static sources are shown on the screen. We can see that for first-order ambisonic format, FOA, the best feature is S log-mail 44. For mixed-array format, the multi-channel log-mail and multi-channel log-mail GCC FET give similar results, but not very far away from the single feature S log-mail 44. These results are consistent with the 2019 SELD challenge results. The experimental results for dynamic sources are now shown on the screen. For FOA format, the best feature is again S log-mail 44. For mixed-array format, the single-channel inputs now outperform the multi-channel inputs by a large margin. The experimental results for FOA format are now shown on the screen. For both static and dynamic source, S log-mail 44 is an undisputed winner. One of the reasons why single-channel input features are better than multi-channel input feature for SED of FOA format is because the dual information are encoded as magnitude of the omni X, Y, and Z channels, so the spectral content are distorted in the X, Y, and Z channels. Therefore, when we use the feature as an input feature, the model will easily be overfitted. Experimental results for the mixed-array format are shown on the screen. It is unclear why multi-channel features are better than single-channel features for static sources and vice versa for dynamic sources. One possible reason is because there are more changes in the signal in the dynamic source cases, and the model trained with multi-channel input overfit. Furthermore, the model that use multi-channel features are slightly larger than the model that use single input channel feature, so they are easier to be overfit to small dataset like 2019 and 2020 SELD dataset. The experimental results for all single-channel features are now shown on the screen. The best uses of single-channel feature is to train the model with all the single-channel log-mail spectrogram as separate training samples, and during inference, all 4 single-channel log-mail spectrograms are used as separate inference instances, and the final result is the average of all the inference outputs. The experimental result for all multi-channel features are now shown on the screen. For FOA format, multi-channel log-mail spectrogram is a clear winner. We should not use intensity vector to train SED models. For mixed array format, overlay multi-channel log-mail spectrogram is also better than a combination of multi-channel log-mail and GCC FAT. In conclusion, for small datasets, multi-channel log-mail spectrogram and spatial features such as GCC FAT and intensity vector are not as good as single-channel log-mail spectrogram for SED. The implication of this study is that for SED application that require small network, quick inference time, and single-channel log-mail spectrogram is sufficient, and for SELD model that use the same input feature to jointly train SED and DOA estimation, this combination is not optimal. The remaining question for this study is that it is possible that the stacking mechanism that we stack spatial features with multi-channel log-mail spectrogram is not optimal for cell event detection, and we need more study with larger dataset to confirm the finding in this study. Thank you very much for your time, and hopefully to see you in the live Q&A section.